Okay, and Niels Warburton is our first speaker on post-adiabatic waveforms. Thank you.
Okay, thank you very much. It's a great pleasure to be here to present results on behalf of this Multiscale Self-force collaboration. I'll introduce the members at the end. This is going to be a pretty kind of lightning tour of all the updates we have, so I'm happy to take the questions afterwards as well. Okay, so what are we doing? What's the motivation here? Well, we want to produce waveform models for extreme mass ratio inspirals. These are going to be tens to hundreds of thousands of cycles whilst in the least band. And during this time, they're pretty much always orbiting in the strong field, deep in the strong field. So we can't make use of post-Newtonian theory, because we need to know these waveforms very accurately to track their phase across many years and all these cycles. And the length scales in the system, and the time scales involved, means we can't use numerical relativity. It's very expensive to resolve the small secondary when it's thousands of times smaller than the primary, and we also have to resolve hundreds of thousands of orbit. We're not doing that with NR, we have to use a different approach. And so instead we turn to a different perturbative approach. We make use of the fact that we have a small body and a large body, and the mass ratio is a small number, and we can do an expansion. And so we expand the metric of the binary around the dominant metric of the primary, which in this case will be a Kerr black hole plus first and second order corrections, and we think that's enough that we'll need for at least for EMRI science. And then the name of the game is to sort of stick this into the Einstein field equations and solve order by order. As I go for this talk, I'm going to use a bunch of different mass ratios, so just quickly define them. I'll normally talk about the small mass ratio epsilon, which is the mass of the secondary divided by the mass of the primary. We'll talk about the inverse of that, the large mass ratio, which we'll call Q. Sometimes use the symmetric mass ratio. And if we have spins, then the spin magnitude will be chi I. Very quickly, to give a sense of what we actually do in the multiscale approach, here we make use of the separation of timescales, so the orbital timescale is much shorter than the radiation reaction timescale. And we can have, at least on the geodesic level, we have constants of motion, these JA, which is the mass and spin of the primary black hole, those are evolving in the geodesic case, and the energy, angular momentum, and Carter constant of the system. And there are associated phases with those, which are the integrals of some frequencies. And so we can actually write down the evolution of the evolving binary like this once we allow back reaction. So the phases are just the integrals of the frequencies, and then these are constants of motion, or they're constant when epsilon is 0, but then we allow them to drift due to back reaction. And these forcing terms are known as the adiabatic or 0 PA term, and there's a post-adiabatic correction to that as well. And so what we need to do is compute these quantities. The way we do that is we write the metric perturbation down as a product of slowly evolving amplitudes and rapidly evolving phases. So we factor it like this. So we have the spatial dependence here, but then all the time dependence is in the evolution of the J's and in the rapidly evolving phase. We can treat these two times as independent and do a chain rule expansion in order to handle the derivatives that appear in the field equation. So we take this, we substitute the Einstein field equations, we expand this out, these two related to these, and then you calculate for the next 10 years, and you get the answer. So I'm going to brush over all of those details. That's how long it took. And then what you get is the following scheme. And so one thing I really want to emphasize is that we have a native fast-built waveform generation scheme built in. We do not need to calibrate other models or build surrogates. We can build rapidly EMRI waveforms from this whole procedure. The way that works is there's a very expensive offline step where we have to compute all of these amplitudes and solve the field equations. That's extremely computation demanding. We have to fill out whole parameter spaces on a grid of these constants of the motion. Once we've done that, we interpolate it, and then online we can compute things very rapidly. We solve these ODEs, typically 10 milliseconds. We have to add up all the amplitudes and sum them, and it says a bit cut off here, but it says it should be a 2-year-long waveform. We can compute 900 milliseconds when we use this fast EMRI waveforms package that Michael Katz talked about on Tuesday, and Zach Nasipak is giving an update about that tomorrow. Okay, so the rest of the talk is then a bunch of updates about how we compute these various things and the latest where we are with computing different waveforms. So once you include these two leading forcing terms, so the 0 PA and the first post-adiabatic correction, then the error in the waveform phase scales as the small mass ratio. So if you have a very small mass ratio, your error in your waveform should be very small. A few years ago now, we completed the first post-adiabatic calculation, and we showed that, perhaps surprisingly, we can agree very well with numerical relativity, even at mass ratios of 1 to 10. That was for non-spinning binaries. We pushed that forward, a recent work led by Josh Matthews. We've extended this to a slowly spinning primary and arbitrary spin on the secondary. So here is an example, and you'll see a few plots like this. What we have is a numerical relativity simulation in black, And then this is for some SXS. This is a mass ratio of 8. The spin on the primary is small, 0.08, and then we have arbitrary spin, high spin on the secondary, 0.078. And you can see that in orange, the self-force waveform, the post-adiabatic waveform, beautifully tracks it, even including right up close to the merger, just the last few cycles that we don't capture in this post-adiabatic expansion. So we're pushing away from just doing non-spinning systems. We're not yet ready to do a fully spinning primary, although we are really epsilon away. I would say we're very close to having that done. I'll talk about that in a bit. But in the meantime, we've developed this new set of models, which are known as the Wasabi hybrid models. So this is something that Josh came up with, the waveform simulations of asymmetric binary inspirals. He's currently based in Asia and loves wasabi, and that's where the name comes from. And you'll see a family of these models will appear, but the first one is the circular model, so this is for the wasabi C. The idea here is, well, we know, this is the equations we're trying to solve, but for a quasi-circular case, let's pick one piece, like the flux. We have a leading order contribution and a second order contribution, and then higher order terms. We know these pieces fully accurately, but we don't have the pieces that have spinning corrections in yet. We haven't computed those, but we can fill those in with post-Newtonian information. And the reason we can do that is we don't need to know these terms as accurately. They don't cause that much error in the phase. So using PN with a little bit of resummation, we can incorporate all of this information. That might be important as we push to fully generic parameter spaces where we might struggle to finish the post-adiabatic corrections in time. That seems to work beautifully. Here again is another example. So again, in black with numerical relativity, this is a mass ratio of 6. But now the spin on the primary is much larger, minus 0.04, so it's retrograde. And the spin on the secondary is 0.8. And again, you can see the self-force waveform. So the black is NR, and the self-force waveform is beautifully tracking as the blue curve now, right up to close to merger. So we'll be able to cover more of the parameter space. That, of course, is just one waveform. Maybe I'm just showing you the best one. But we've done a study of this. Looking at the mismatch, this is just in the 2-2 mode between a suite of NR simulations, but also SEOB and TOB, the two EOB models. We're covering quite a decent chunk of the parameter space we've looked at, and we find that we're basically competitive with those models across that part of the space. It's just the inspiral that's important to clarify. We're not doing merger ring down yet. And we think we should be able to outperform those models at Q greater than 20 by comparison with them. And that's really because they're not including good zero PA information. They're using PN, we're using the fully correct numerical data there. So that's how we're pushing towards Curt, but I'll talk a bit more about that in a minute. One other thing that's been making a lot of progress, so here we fill this in with post-Newtonian information that we have. But it would be great if we could get higher order post-Newtonian information. And as we know, grinding through the PN orders takes a long time, it's very hard. But there's promise that we can do that quicker, or get higher orders in self-force as well. There's big progress there. So we'd like to compute more PN orders, more than the 4.5 that are known, that took many years or decades to get to. But we know that if we do a double expansion in PN and self-force, so expanding in low velocity and in the small mass ratio, we can reach very high PN orders at leading order. So if this leading order piece in the flux, we actually have 22 PN that people are able to calculate. Just very recently, the framework has been built to actually start computing the second order correction within the self-force framework, doing this double expansion. And then just like maybe last month, they've completed the calculation, they've got the leading terms. They've managed to reproduce the quadrupole, which is great. But now they've hoped to be able to kind of push up the orders, and maybe that will allow them to push beyond 5 PN, 6 or 7 or something. That will take time, but that will then build into this Wasabi model where we can kind of fill in these post-adiabatic pieces from post-Newtonian self-force. So they've made a lot of progress here. This is just showing one of the nice things they can do because they're fully analytic. When you do things numerically, you have to sum up all the first order modes and couple them together to get the second order source. This converges extremely slowly if you do it numerically, but of course analytically you can just compute this thing exactly. And it's divergent, and you have to cancel that divergence and regularize. But I think this is going to be big in the future. It's going to be very important work. Okay, the other thing you'll have noticed is in all the comparisons I made with numerical relativity, we didn't have a merger and ring down, because that's because our multiscale expansion breaks down. We rely on the fact that the inspiral time is different from the orbital time period. But there are new timescales that appear as you transition to the plunge, and so we can do an expansion on that timescale instead. So we get a transition timescale, and there's also a timescale for the plunge. And so we can build all the same kind of calculations, and it fits into the same fast waveform generation framework, and add on a merger and ring down to our waveforms. So there's recent work led by Lorenzo Cutler, and here's again a comparison of numerical relativity. This is showing the plunge. The dashed here is numerical relativity, and then that you see the matching of the plunge to the self-force waveform looks really nice. Again, this is Q equals 15. So it looks very nice. This waveform, this NR waveform is picked so that by the time it merges with a remnant with 0 spin. So that's one of the things that we're restriction for the moment. And then just very recently, this has now all been incorporated into the fast memory waveforms package, and we have a few IMR version that should be coming out in the next few months. And here again, this is a mass ratio of 25, where we don't have NR simulations, but we do have the ability to run the phenom and EOB models, and we're nicely tracking the waveform during the inspiral. And then there's a little difference as the merge and ring down between the models, but the Q equals 25, we still need to assess which one is probably the best there. But the basic idea is that we'll be able to do full merger ring down within this framework as well, maintain fast generation. It's probably going to be important for intermediate mass ratio in spiral modeling. Okay, as I said, we're using these Wasabi models to push towards the Cur case, but we're actually directly going to compute the fully self-force calculation in Cur. And here, there's been a lot of progress. I was literally checking Mattermost before this talk because we almost have it. I could have had a different slide just a few hours ago. Big push on this. So in order to tackle the Cur case, we've had to completely retool the second order calculation. The first calculation we did relied on the spherical symmetry of the spacetime, so we had to relax that. We explored a bunch of different approaches from Tucholsky and various things. Yeah, we've settled on something where we're solving for the full metric perturbation, but now decomposed into M modes. So spherical harmonics don't make as much sense in Cur. And so what we end up doing is a decomposition like this. We factor out the azimuthal dependence, and now we end up with an elliptic PDE that we have to solve for R and theta. What's great about that is we've then connected with people using Spectre codes, and we use their initial data solver. They're really good at solving elliptic PDEs for their initial data. And connected those two communities together, and that's been fantastic because we've made rapid progress. And we now basically have a full framework set up to do that. So there's a paper very recently showing this in the scalar field case, and this is a nice example. So they're using the Spectre code, but with a self-force source. They're regularizing in this region of the space-time. It's doing all this adaptive mesh refinement, and we get a really nice calculation of the scalar self-force. They have a fully working version for the first order metric perturbation. The paper is coming, and second order is honestly hours away at this point, so it's very close. I think they're trying to get things ready for the CAFRA meeting that's taking place next week. So I think watch that space. That's it. There's a lot of updates. There's more that I haven't had time to talk about. This is the collaboration. So we have a pretty recent website if you want to check out, selfforce.org. There's now about 20 or so people working in the collaboration, plus we have about another 20 or so associated members. Thank you very much.
That was a great talk. Any questions?
You want to turn on the mic?
So for these
Wasabi,
for these Wasabi models, you are averaging with PM. Can you do something similar for PM, especially to cover eccentricity and
With PM?
yeah, if you think it could be possible to do?
Yes, we have been exploring that. It's not clear to us how useful the PM is, more than PN itself. So it's something we are looking at.
Even for large eccentricities?
Even for high eccentricities, yeah. So there is a development of a Wasabi E model, which will just be Schwarzschild, I think. That's going to just use PN to begin with. But there's a separate group of us looking at incorporating PM information. But preliminary results don't suggest it sort of really helps you get to high E.
Yes?
Yes.
I was wondering what is the goal here? Like at which accuracy we will say that maybe we don't need to calculate the further orders.
Yeah, so we know from multiscale analysis that we just have to incorporate these first two terms. And then, as I said here, the error in the waveform phase scales as order epsilon. So 10 to the minus 5 mass ratio, the error is 10 to the minus 5 radians times an unknown coefficient, but it's small. And so we think that's enough. But for EMRIs, there's some evidence that for EMRIs you might need 2 PA, but that's going to be okay, we think, because what we will do is exactly what we do at Wasabi. Eventually we'll have this knowledge complete at 1 PA, and then you'll use PN information to fit in enough of the 2 PA to model intermediate mass ratio.
Just one more question.
Just real quick.
So these waveforms, from the self-force side at least, would automatically have the higher modes, right?
Oh yeah, we don't talk about higher mode models.
Right,
We have,
it's just there.
yeah, we have mode of del equals
I
30.
don't see them, any evidence of them here.
Oh yeah, so I guess just for this short talk, we focused on the 2-2 mode. But if you go look at the papers, the comparison of NR got to the 5-5.
Okay, so it's got all of those.
Yeah, we have all the modes. Okay.
Okay, thank you very much.
Thank you.
Mudit. Thank you.
Next speaker is Mudit.
So again, so my name is Mudit, and if I did not have a pleasure to meet you, then it has been a great conference. And so today I want to talk about this project which we recently finished, and it's under review at UpJL. And the idea is to consider turbulent flow in accretion disk and how they affect EMRI waveforms. Thank you. So I'm a postdoc at NYU, and before that I was a student at University of Zurich with Lucio Meyer. So I think at this point I don't need to convince you what EMRIs are and how they form. But let me talk a bit about gas. So Francisco in his talk covered this a bit, but the idea is that when there is a MBH at the center of galaxy and there is a gas which is pushed to the center by supernova or some other processes, then it can settle into a coplanar geometrically thin accretion disk, which is very well defined by the Chekhov-Sonoyev model. And it actually explains a lot of the observations. However, some gaps remain, like emission variability or spectral signature. The perturber, perturber induce a spiral density wake in the disk. So this is the central black hole, and there is a small stellar mass perturber. And you can see, it's very hard to see, but there is an inner wake and there is an outer wake. So inner wake is the one which makes push the secondary outward, and the outer wake push the binary inward. And overall, in a laminar flow, it turns out to be slightly negative value. So the reason I'm emphasizing on the laminar flow is that in this case, you can see the disk is very smooth. And these simulations, which is taken from the Lisa code comparison project disk EMRI, which I was also part of, are consumed like locally isothermal. So basically the aspect ratio of the disk, how thick the disk is, remains same. And they are highly viscous flow, like alpha of 0.1. And the mass ratio here is 10⁻⁴, and the binary is circular. However, we also know that in reality, the disk can be complex. So if you are talking about a bit of like a bigger scale, like parsecs like scale or 0.1 parsec scale, then there can be gravitational instability. And the inner region where the Lisa EMRIs will reside when they are going from like 10 RS to merger, those are very hot magnetized plasma, and there can be like MHD turbulence, like magnetohydro turbulence, which is generated and sustained by MRI, which is magnetorotational instability. That means that things can look very complex, and their viscosity can be higher than even alpha disk. So what I'm showing you here is a simulation, gravitoturbulent simulation, in which in a laminar flow, I don't know why text is wobbly, but in a laminar flow, there is a secondary, and this is like a positive torque on top and negative torque on bottom, and you can see how smooth it is. But the moment you have turbulence, the things look very complex. That means maybe your linear torque assumption breaks down. So how to model that? And we do not have a very good simulations of MHD for EMRIs. So we try to model using the gravitoturbulent study, some kind of qualitative model which can be used to study this kind of system. So the idea is that in laminar flow, we have this like ansatz in which you have Z divided by sigma naught A raised to 4 omega square. So A is semi-major axis and omega is angular frequency, and sigma naught is density normalization. So if we have laminar flow, then Z value is simply just Q by H naught square, which is well studied linear torque. If it's turbulent torque, then we model it like a Gaussian around the linear torque with some width, Gaussian width. And the idea is that in this paper, the gravitoturbulent paper, the gas torque has a lot of stochastic component, but more or less it oscillates around the linear value. And if you draw it like a histogram, then the more turbulence you have in the system, the more this Gaussian width becomes bigger. So in their paper, they explore different alpha and H naught, and they fit this kind of model in which if you multiply this sigma Z with the sigma naught, big sigma naught, then you have this kind of formula in which you have dependence on alpha and H naught, So the more alpha is more viscosity and more scale height is also giving you more width. In this paper, we introduce another, what happened? Oh, it's back. In this paper, we also introduced this parameter C, which is controlling whether the real turbulence is weaker or stronger than this paper. And so in this figure, Z, like C equal to 0.1 is like V turbulence, the green curve, and the C greater than 1 is like a strong turbulence. And another thing I want to bring your notice to that because these things, whenever there is this instability that grows very quickly, and it takes some time for it to resolve. That means it's possible that you have the same sign and magnitude for some orbits, and then suddenly it changes the sign and magnitude. So basically, if we are modeling EMRI motion, we can say that, okay, if we draw something from the uniform distribution 1 to n max, and n max in this paper is 100, we will also explore other values. Then it draws a new value, and those are the value where the Z parameter will remain same. So this is the basic of this modeling. So we are going to consider two isothermal, locally isothermal disk profile. One is viscous disk, which is more applicable for this paper, which is gravitoturbulent, and also the radiative disk, which is radiation-dominated disk, which is more applicable for close by EMRI. So like those people who know accretion disk, there are like different region of the disk depending on whether the gas pressure is important or radiation pressure is important. Now the idea is that one is that there is a torque application, but how does it affect the EMRI waveform? So we don't have very good models for that, so we will do some simple modeling here also. So if you do just a simple Newtonian torque balance of this T gas, then you can say that the SMA, semi axis changed by the gas, is given by this formula. And then if the value of this formula, I don't know, sorry. If the value of this, this Z is positive, that means with respect to gravitational inspiral, it's slowing down the inspiral. And with respect, if Z is negative, then it's speeding up the inspiral. Because we don't have any good simulations where gravitational wave is important component together with gas for a long time, so we get the most simple thing we can do is that we can linearly add these effects. And because A dot gas at any given instant is like 100,000 times smaller than A dot GW in the LISA band, so maybe this approximation is good enough. But I will discuss about it slightly in the end. Then there is something called stationary phase approximation. The idea is that in 4 years of LISA observation, the mass of the binary will not change appreciably. However, that means the amplitude will not change, but your phase can have more this kind of sensitive to this kind of perturbation. And that will mean that as the binary is evolving, you will start seeing the difference between how the gravitational wave should look in vacuum with respect to gas. The merger part will remain same. That means that can act as a reference point, and then you can see how many cycles you have lost if you backtrack in the data. So dephasing is simply this, and because your torque is like a Gaussian distribution, your dephasing will also be a Gaussian distribution. And if that value, so in reality, we will only see one EMRI system in gas system. That means your final dephasing will be a value drawn from this Gaussian distribution. And if that value is more than 8 by SNR, which is a typical first order order of magnitude estimate, like whether this dephasing is observable, then that means that at least LISA has hope to see them. So in the paper, we go through some calculation, but the idea is that the linear torque value is just a standard value. A0 is the initial separation, AF is the final separation. And then for this formula, for our complexity where the value is changing every few orbits and we are drawing a new distribution, we approximately derive this, and this analytical formula is only like 10% error from the numerical one if you do it properly. And for the result I'm going to show for the golden EMRI. The idea is that it's a Milky Way like black hole where a 50 solar mass black hole is falling in, and it will have like a 50 SNR, which is like typically on the upper end of EMRIs. And so the idea is that as the mean of the turbulent dephasing is same as the linear dephasing, so most likely you will see that value. But in a realistic manner, the maximum you can see is like +2 sigma, the width, divided by this critical parameter. So if this lambda term is more than 0, that means you have observable dephasing. If lambda term is negative, then you don't have that, and we also show the linear one. So first I show for the viscous disk, and there is a lot going on, so let me just quickly summarize it. Each panel, I'm changing the aspect ratio and the alpha, And for overall, I'm changing whether the torque is changing every, Nmax is 1, 10 or 100. And on the y-axis, I'm changing whether the C value is 1, 0.1 or 0.01. And in each panel, you can see this dotted line, which is the linear torque value. So 0 is the value where linear torque was already observable. And then you can see that for some parameters, you can see this turbulent torque is opening a new parameter space, which was previously inaccessible. So this is to say that because of turbulence, it's possible that you have dephasing, which is more than you have before. Of course, it can go other way also, but just to show the most optimistic case. Same for the radiative disk, is mostly this panels where the things are opening up. So this is to say that if the torque is changing every like 10 orbits, then you have some new parameter. If it's changing every 100 orbits, then those things are observable in turbulent dephasing for all parameters. Yeah. And for LISA, because the radiative disk or radiation dominated disk is more likely, that means that all these green panels are showing you that, okay, the things we thought were not possible are possible here. And this is not to say that this is like the reality. It's more like I want to make an important point here. The main takeaways from this talk is that we need long MHD simulations of embedded BHBs to understand MRI-driven turbulence. So unfortunately, I have to use gravitational turbulent disk because we don't have good models. So right now, for various reasons, people model EMRIs in gas which have laminar flow. But because we want to capture reality with LISA, we have to have MRI. And this is something I'm trying to work with. I'm working with Yanfei Jiang at CCA, trying to do MHD turbulence studies. We need to simulate GW-driven BHBs in a disk for longer time. So either we have simulations like 2D viscous which don't have gravitational wave, or we have GRMHD which are like a couple of days away from merger. But there is a middling regime which is very rich because LISA will see these binaries for 4 years. And I've written a couple of papers on it using Gizmo code where we try to couple them and we find that dephasing is actually different than what you find with linear addition. Another thing is we need to understand how having turbulence in your disk can affect your rate prediction. So most of the rate prediction for EMRIs or LIGO in gas disk comes from assuming laminar flow. But if you have turbulence, that means your migration traps may not exist, or they may not exist in their current form. That means at the expense of LISA LVK binaries, you can have more EMRIs. So thank you for your time, and I'm happy to take any question.
Any questions? Well, I have one then.
Yeah.
So I'm ignorant about this, but thank you. So the question is, usually when I hear turbulence, if it's in 3 dimensions, I hear Kolmogorov spectrum, right? And I was wondering if in this case where it's sort of 2 dimensions and you get a magnetic field, whether the same sort of argument can at least tell you what the spectrum looks like.
In the magnetic fields?
Yeah.
I've not thought about it, so it's very hard to say about this one. But I think in this work, it's more about just trying to model the stochastic nature of the torque. So I'm not aware of this Kolmogorov.
Oh, okay.
Yeah.
Okay.
It's not exactly Kolmogorov feeling in systems.
Yeah, so but is it a place to start was the question.
Yeah, I think assume so.
Hi.
Yes.
Hi, thanks for the great talk. I just have another question for computing this torque. So if we think about the small black hole flying into the disk, we have 2 components that can just drag on this object. The first one is a momentum accretion directly falling into object.
Mm-hmm.
But we also have an asymmetric mass distribution around it, making a net gravitational drag.
Yeah.
Which term is actually dominant for the torque you're using here?
Gravitational.
It's gravitational.
Yeah.
And is there like any analytic argument that this momentum deposition directly onto the creator can be neglected?
No, so the idea is that we are looking at a system which are like evolving LISA for 4 years. So if your accretion rate is Eddington rate, it will not accrete appreciatively on 4 years. So we are talking about like 10 to minus like 8. So stellar mass is like 10 to minus 7 solar mass per year. So in 4 years, you are not accreting anything significant. Mm-hmm. But the perturber will introduce this wakes in the gas flow, And because of the asymmetry, you will have like a different kind of torque from different direction. And that is the main component which will affect the trajectory of the secondary.
I think my recent understanding is as soon as you avoid spherical asymmetry of accretion, this Eddington limit can be actually very easily circumvented. So I don't know.
I'm happy to chat more,
Yeah,
but
yeah.
I think in 4 years, I don't know how one can argue that it will accrete significantly, but I'm happy to chat.
Sure, thank you.
Any other questions? We have time for one more, maybe? Well, if not, let's thank Mudit again.
Here you are.
Our next speaker is Abhishek, who's going to be talking about surrogate models.
Hey everyone, I'm Abhishek. I'm a PhD student at UMass Dartmouth, and I'm going to be talking about work I've been doing with my supervisors Vijay Verma and Scott Field, as well as some collaborators you see here, on using surrogate models for trajectory flux calculations for the FEW framework. So, to begin, I'm sure all of you are aware of how cool EMRIs are. And LISA intends to, well, we expect LISA to detect maybe too many of them. And so to get any cool science out of them, we need efficient waveform models, well, accurate and efficient waveform models for analyzing the data. Now, the waveform model that I'm going to be talking about comes by virtue of the fast-dummy waveforms framework, which many people more knowledgeable about them than me have talked about. So I'll focus on the part that concerns my work. The general wave looks somewhat like this, where I'm going to be talking about this phase over here. As you know, dephasing can really dominate waveform errors, and so you'd like your phases to be as accurate as possible. Now, in the case of FEW, how they calculate their phase is they decompose it into a sum of 3 different phases, like a polar, azimuthal, and radial. The individual phase evolutions occur based on these fundamental frequencies, which are known functions of some parameters here, the spin of the primary, the semilattice rectum eccentricity, and the inclination of the secondary. And so we need the evolution of these in order to get the phases. How do these evolve? Well, at this point I should mention that FEW works, at least currently I believe, at the adiabatic order for equatorial orbits. So the inclination is fixed at in the equator, and so you will see all mentions of xi drop from here, as well as Carter constants. The remaining stuff, we have P and E that evolve like this. A is constant again at this order. And so you have 2 equations here, 2 equations for the phases, evolve them, time step them, cool, done. Well, if only. The issue is that these 2 terms need to be evaluated numerically from the Tucholsky equation. The bigger issue is that since this is on the right-hand side of an ODE, this has to be done at each time step, and no one wants to deal with the Tucholsky equation once per time step. So instead, what FEW does is the following. It uses splines. So here is a view of the parameter space, the 3-dimensional parameter space, shown as different constant A slices. What it does is it maps this to a uniform cube, well, not a uniform cube, a unit cube, sorry. Constructs a uniform grid across this, shown as these red points here, and then it constructs tricubic splines over the energy and angular momentum fluxes. You get the point. Currently, the good thing about this currently is that it's very fast and it's very accurate. Currently, these things evaluate at like 100 nanosecond evaluation times, which is ridiculous. And accuracy-wise, dephasing is around 1e-4, which is a lot better than what's needed at 1e-1. The issue is that we might not expect this to keep happening as we increase parameter space dimension. So as we start including new physics, including the secondary spin, generic inclinations, the parameter space dimension goes up, and with it goes the calculation costs for splines. So the uniform grids that we need to evaluate get a lot more expensive to perform the Tucholsky solves on. Splines become huge, they might take more time to evaluate. And so overall, we might need a better solution to scale for higher parameter space dimensions. The solution we propose, or we think should work, is surrogate models. So surrogate models are reduced order models. They essentially take a set of data in sparsely sampled in parameter space, and they try to learn what's in between them in parameter space. As some of you might know, this has been used to very successfully for modeling things in the comparable mass regime. But we think it can be extended to the extreme mass ratio, at least in this sense. The advantage, we believe, is that these are made to work on sparser data, and so we don't need uniform grids. But also, so I guess to elaborate my point, I have shown here the example of the surrogate NR Heibser 3DQ8, which is trained on the aligned spin subspace of comparable mass regime. And shown here is the parameter space for this surrogate, with every point representing a numerical relativity simulation for which the surrogate is trained on. And there's a bit less than 100 simulations here, and that's all it really took to model the three-dimensional aligned spin subspace up to mass ratio 8. So it's pretty efficient at what it does. And also, what it can do is the surrogate modeling methodology was used to find these points themselves. So what was done was you started off with the 8 points on the boundaries, and you use PN, a model made from PN, which we expect to be less accurate than NR, to construct a surrogate model over the parameter space and find the point worst approximated by it. You add that point into the data set and you keep going iteratively. Because it's hierarchical, this takes less computation than you think it would. The result is you get a set of points where you know you should send your computers out to do NR simulations for months. And this is effectively a fairly efficient way of exploring parameter space. And so we think this might transfer over to the flux calculation case. Our hope is we start off with a very coarse grid of fluxes numerically calculated in the 4D parameter space, thanks to the few devs. We create a spline over this, and we use this spline as the approximate model to then explore parameter space and figure out the points where we need to we need to recalculate fluxes for the final model. This is done by effectively finding a reduced basis and then finding these things called interpolation nodes. Once you have these interpolation nodes, we can send them off for the flux calculation at these points, and once we have the fluxes at these points, we can construct a final surrogate which should use this finer data set for a complete model. Now, that being said, we are nowhere near the 4D case currently. We start off with the simplest case and try working upward to see how good we can get things. And we're currently at the simplest case, which is the 2D version of this, which is the slice of the data nearest to the Schwarzschild data. And I can show the results for that. So shown here are errors in cross-validation errors for both the spline used by few currently in blue and a surrogate that we've made in orange for the energy and angular momentum fluxes. This is over cross-validation, where you downsample the grid and you train on a subset of the grid. And as you can see, we aren't comparable yet to the spline. It's pretty hard to beat a spline on a uniform grid of data. But we're still doing pretty good. And the good news about this is because we calculate these fits using a Chebyshev basis, we get a basis out of it, which we can then use to find the interpolation nodes. So these are nodes that the empirical interpolation algorithm identifies as effectively being worthwhile to go back and run more simulations at. So yes, the hope is you find some grid like this, perform more flux calculations here to get a final surrogate. So that's progress so far. For future directions, we intend to try finding better basis functions. I don't think Chebyshev is the final goal here. And we definitely need to both optimize fit construction and evaluation so that we can scale well to 4D and so that the final surrogate performs fast, sufficiently fast in the final model. So yeah, that's my time. Open to questions.
It's pretty early, so we've got quite a bit of time for questions. Anything online? No.
Hi, thanks for the very nice presentation. I would like to, sorry because I arrived late and maybe I didn't catch, but what is the advantage of doing a surrogate model of the flux for which you already have a spline?
Well, I guess the point is that, firstly, the spline needs, so there's two reasons for surrogate. One is parameter space exploration itself. The spline isn't going to tell you which points in parameter space to look at, right? The data needs to come from somewhere. And so the surrogate lets you figure out where in parameter space you need to do your flux calculations numerically. Secondly, while in 4D, well, I guess related to that, the splines require uniform grids, and because uniform grids in 4D becomes way too computationally expensive, a surrogate would help with that. And also, as you scale the dimension up even past 4 splines, even if you could do it in 4D, become just...
But you can do multi-dimensional splines, right? I'm just trying to think, it's just a matter of, because you have to store too many coefficients at high dimensions, is this right?
Yes,
okay.
Yes.
Okay.
Other questions?
So you're using a Chebyshev basis?
Yes.
What other bases can you use? So one of the disadvantages of Chebyshev is global.
Yes.
So one data point goes bad, and then
Yeah.
that causes problems. Can you do local?
Yes, it should be possible to do local ones. We haven't really, that's one of the things we're thinking about. We don't really have a choice yet, but some kind of grid-free mesh refinement kind of thing to construct a local basis should be possible. Yes.
So other kinds of splines are local.
Yes.
Splines only use the neighboring 3 points.
Right.
Not local.
Right. I guess splines are local, but they're, in some sense, like if you have a grid, then they're too local. There's too many points you have to consider. Like if for a given point, you only need the neighboring points, but there's so many in the grid that it just becomes infeasible to keep doing it. So if you have a way of mesh refining, essentially figure out where you need larger or smaller sizes, then that would be more efficient than just a uniform spline.
Other questions? Well, if not, let's thank the speaker again. Thank you very much. Next speaker is Dan Oliver.
Okay, my name is Daniel Oliver. I'm a postdoc at Oregon State University, and today I'll be telling you about our project on quantifying detectability for EMRIs that merge after the mission ends. So as motivation for this, we've heard a lot about EMRIs so far, but EMRIs are very long-lived signals that can have tens to hundreds of thousands of cycles in band. And so that means that there are quite a few EMRIs that might not merge within the 4-year or potentially 10-year mission lifetime. And for these signals that do not merge within band, you likely are going to have a separate detection strategy. And to illustrate this, I have 2 figures at the bottom that are both time frequency plots. That is an EMRI that merges within 4 years. You can see the harmonics swooping up, as you expect. And then an EMRI that merges at 20 years, but you still only see 4 years of data, so it's just horizontal lines. So I am not giving you that detection strategy. I don't know it. But what I'm going to do is quantify if this is actually an issue. So the way that we're going to do this is we start with a population draw. We draw 4,000 EMRIs from astrophysical priors. We compute the trajectories with each one of those using fast EMRI waveforms. So we start with a final eccentricity at plunge, and we integrate backwards to some time to plunge of 20 years and determine our parameters at each of those points. We do 72 total grid points for our time to plunge, and then we compute our waveforms. So again, we use fast EMRI waveforms, and we use time delay interferometry for all 288,000 combinations for each of our models. And then for analysis, we show 2 different types of figures, our detectability fraction versus time to plunge, as well as the SNR versus time to plunge. So I'm not going to go through all of this, but our full parameters are on the left, as well as some of the details for our waveform model and SNR on the right. The key thing is that this is based off of the M1 model from Babak et al. 2017. It's not entirely that model. We also look at a second model that we're calling M1 heavy. And the main difference is the secondary mass. So in M1, you have a fixed secondary mass of 10 solar masses, and our M1 heavy, you draw uniformly between 10 and 30 solar masses. Now, the other big thing that we do that is different for this model is we attempt to work with inclination. So Fast Fermi Waveforms package only does Kerr equatorial eccentric. So equatorial means no inclination. But if you define your your spin, your A, as some A max value times cosine of iota, where iota is your spin parameter, your inclination, then that will adjust your spin, and it kind of emulates what an inclined orbit might look like. To test this, we actually compared to the Fast Fermi Waveforms AAK, the augmented analytical kludge, and found that they were agreeable enough that we felt comfortable doing that. Now for our trajectories, I have this figure here that is simulatus rectum P versus orbital eccentricity E on the y-axis. And then we have the separatrix or the plunge in this dashed line here, and we integrate our trajectory backwards for different times to plunge. So again, 72 total grid points. We have more points where we are in the first 4 to 10 years, and then it gets more sparse as we go out to higher plunge. And the reason why is we compute the waveforms for every single one of these. So as we get out to the 20 years, computing a lot of 20-year waveforms still is computationally expensive. So let's get into the results now. For the 4-year LISA mission, we're going to look at 2 different figures. So on the left is SNR versus time to plunge. And then on both of these, there is a vertical dashed line that denotes the 4-year mission time. And you can see the median in this dark purple, and then the 5 to 95% band in the light purple. This is all of the points from our 288,000 waveforms. So the SNR here is actually not that substantial. So the median SNR is around 1. But if you go up to these higher ones, the SNR is quite a bit larger. If I show the full 100%, this goes from 20 SNR to around 300. So just to kind of show a bulk of the sources, I just chose this 5 to 95% band. And then on the right is our detectable fraction in percentage. And since we don't really know what the SNR threshold is going to be for EMRIs, we show 3 different SNR thresholds. In green is SNR greater than 10, in blue SNR greater than 20, and in red SNR greater than 30. So the key thing to get here is that at the very beginning, if an EMRI plunges right at the start of the mission, you don't get a lot of SNR. It's not likely to be detectable. It doesn't have that time. But then very quickly, you start to get a high detection percentage, and this kind of levels out a little bit with a gradual increase until just after the mission ends. So at 4.1 years, you now miss the merger, and the merger contributes a lot of SNR to your total signal, and so you see this now greatly drop all the way out to a time to plunge of 20. So we then decided to look at what an extended LISA mission would look like. So a 10-year mission. If you look at the left actually ends up looking about the same. So for the sake of time, I'm not going to cover that too much. But the right is very interesting. So this is, again, detectable fraction versus time to plunge. And if you just look at this green one, the SNR greater than 10, it increases as you expect. And then right at 10 years, it drastically decreases. But look at 20 years. That does not decrease to 0. And if you are keen-eyed, you might have noticed the same thing at the 4-year case. 16 years after the mission, this EMRI emerges, and it's still detectable. So that makes you think, what's causing that? So we looked at this detectable tail, and it is exactly what you would expect. On the right, the tail survivors are the ones that are close by. SNR and amplitude scales with distance, so the close by sources are going to be louder, more SNR. But what we have on the left is just combining those detectable fraction plots for SNR greater than 10. And I have on here the percentage of detection at different thresholds, so 4-year and 10-year. And this is for the orange is 10-year mission, 4-year mission is purple. But the interesting thing again is at 1% of the total EMRIs are still detectable at 20 years for the 10-year mission. That's 40 EMRIs, which doesn't sound like a lot, but that is not an insignificant number. And then that brings you to the so what. Well, what does this all mean? Does this matter at all? And for that, we have this nice table. So this is the mission duration, 4 years, 10 years, and then the 3 different SNR thresholds, and then this beyond mission share. So this is of all of the EMRIs that were detectable in this model, what percentage of them merged after the mission ended? And these numbers are kind of high. So if you just take a sort of median number here, around 25%, that is 1 in 4 of the EMRIs that are detectable merged after the mission ended. So those 1 in 4 need a potentially different detection strategy. So that is kind of an interesting thing, and this should definitely be followed up. But to go ahead and summarize here, again, EMRIs that merge after the LISA's mission lifetime are still likely to be detected from just the 4 years of building up SNR while in band. We quantify that detectability versus time to plunge for both the 4-year mission and the 10-year mission. And then the sources that make up this long detectable tail are likely to be close by EMRIs. And since we don't know how many EMRIs there are, we don't know how many are going to be close by. This could end up being a worse issue or a better issue, depending on your perspective. And then merging and non-merging signals are likely to require these different search strategies, and they should be accounted for in data analysis pipelines. So thank you, and I will take any questions.
Thank you, Daniel. Questions? No. Questions from the floor? Okay. Well, thank you very much for your talk. Our next talk, our last talk of the session is by Gabe Freedman.
All right, thank you everybody. So throughout the session, we've heard lots of very interesting talks about different improvements and changes and other things to EMRI waveforms or other things that we need to account for in our data analysis pipelines. So then to close out the session, I'd like to sort of bring your attention to the data analysis pipelines themselves and what sorts of improvements those of us who are working on the LISA Global Fit are working on behind the scenes. Specifically some work that I have been doing in adding in sort of gradient-aware sampling proposal jumps and samplers into our EMRI parameter estimation pipelines. What is the motivation for this exactly? Well, EMRIs are not an easy problem in more ways than one, probably too many to count, one of them being parameter estimation, the very end when we're eventually trying to get out samples and posteriors to you, the scientific community. Why is that the case? Well, it turns out to be a uniquely challenging step in constructing our overall LISA Global Fit algorithm. It's got a very large parameter space compared to other LISA sources. The posterior bulk for EMRIs is going to be occupying some very, very tiny section of our total prior volume. The intrinsic parameters of the EMRI space will be oftentimes highly correlated, and sometimes correlation coefficients or factors of close to 1 or 0.99. Particularly up in the intrinsic space, and then you'll see some corner plots later on which will focus on those 5 parameters up in this block here with those very strong correlations being component masses, spin, semilattice, rectum, and eccentricity. And then as far as like a more practical reason why this can be difficult for parameter estimation is that currently our waveform generators, the speed of them really necessitate the use of GPU resources. So we're already restricted in that computational sense that we need GPUs just to get these things to run in the first place. So correlation alone is not necessarily the only problem. There's also the problem of EMRI degeneracy, which is that there are numerous secondary peaks throughout the EMRI likelihood with nodes, these secondary peaks or secondary nodes that can reach injection overlap, meaning the waveforms are, have similarities up to levels of maybe 0.7 or 0.8, sometimes close to the actual injection point, and sometimes at very disjoint regions in parameter space. So this ends up being a hindrance for EMRI searches, and by extension also EMRI parameter estimation. So for the same source that I showed in the previous slide, same injection of about, SNR about 61, I just showed that example over some block of, say, the two component masses gridded up, calculate that overlap at different points throughout the grid, and sort of show that there are, even in this small region of parameter space, there are multiple templates that have overlaps of even just over 0.25 that we have to contend with. How does this end up translating at the very end of this ordeal to parameter estimation? Well, let's say that we do have a fantastic detection or detection pipeline, an EMRI search pipeline, and we're able to set, in this case, sort of narrow priors around where our detection pipeline has claimed to find an EMRI. Of course, I put narrow in quotes because something like that can be in the eye of the beholder in their own pipelines. Then we're able to recover whatever signal we may be looking for to a relatively good degree. However, as we start to extend those priors and maybe we need to search a wider swath of parameter space for the same source, that is when they start to break down and get trapped in either secondary modes or other parts throughout the parameter space. That is where, in terms of our global fit, our stochastic sampling, our MCMCs, we want to look for alternative methods to sort of, find some happy medium between needing these sort of constraints and then this sort of worst case scenario. Why could gradient proposals possibly work? Well, when we're dealing with very correlated parameter spaces, ones where you can consider sort of your posterior as some very fine ridge-like structure, then if you are using MCMC proposals that base themselves off of your gradient of your model likelihood, your posterior, then what it's able to do is find those peaks very well and converge quickly into the posterior bulk, at least quicker than if you were to do sort of a naive Gaussian proposal, which might be the foundation of some MCMC pipelines that you use. Of course, whereas your gradient proposals might have more efficient local convergence compared to the slow diffusion of your Gaussian proposals, are we actually able to move between the different basins? It gets back to this other question of the secondary modes within the EMRI space. Would we be able to have a high enough energy proposal to actually move between them? And that's something we want to try and explore by implementing this into our pipelines. Because otherwise, say we have an ensemble sampler, one might get stuck in the true posterior and one might get stuck in somewhere else. This is about as cartoonish of a cartoon diagram as I would put together of our current Python global fit code. Aaron, how it works, if you have not used it before, you can think of one giant blob at the front that contains all things like your waveform generators that many of us work on, or your response function, things like setting priors, things like implementing parallel tempering, and then you end up selecting what kind of proposal scheme you want for your actual MCMC. Do you want standard Gaussian proposals? Do you want to do some sort of ensemble Walker scheme with stretch proposals between walkers? They've got delayed rejection built into there, and there's plenty of others if you haven't yet explored, and it ends up outputting samples that you can then draw posteriors from. So the work, and then of course also, it doesn't have to be one or the other, you can combine them in multiple different pairings if you choose. But the work done here is to say, can we also implement and build in these gradient proposals into the existing sort of architecture that we've built, and hopefully have them work seamlessly in tandem with the other proposals that we have. So meaning things like HMC proposals, adaptive HMC, nuts, things that if you're not familiar with, they're just examples of sampling algorithms that make use of gradient-based proposals. And the tools used for this type of analysis, we've got, of course, Few, which we've talked about in, I'm pretty certain, every talk so far in this session. For our waveforms, using, again, Aaron as our sort of ensemble sampling backend. And then this fantastic new code that came out last year by the group listed here called Stable, and it's called Stable EMRI Fisher, allows us to calculate basically Fisher matrices for EMRIs, which then, in the case of gradient proposals, means we can now more easily get our derivatives for the proposals themselves. So that's been a great help to implement this into the pipeline, and then the compute resources, like I said, were kind of restricted to GPUs at this point, and that is the GPU that I had access to on my cluster to use. So comparing how the gradients are set up within stable Emery-Fisher against, say, your naive finite difference gradient scheme, you can see that they agree with each other across the parameters in the Emery space over a whole different range of iterations or step sizes. They agree. And then as far as how fast this is going to be, another important consideration when we're determining whether or not to implement this is how fast is the gradient going to be compared to the standalone likelihood calculation. And we get about a factor of 8. Factor of 8 slower for the gradient, which is going to be better than, say, a naive finite difference scheme where it would be the number of parameters, or potentially 2 times that if you're doing a central finite difference. Okay, as far as how this works, take an injection case. You can see the parameters that I used there to create this SNR about 56 injection. As far as setting the prior widths for the couple of analyses that I did, I based them off of, again, this stable Emery-Fisher code, being able to calculate parameter uncertainties from there, and then kind of use that as like your prior half width that then we can extend by multiples of that uncertainty. So it's say 2 times your Fisher uncertainty as a prior half width. Both the gradient samplers as well as our sort of default mode within Aaron, which is using the stretch move, they both converge. I mean, this is a pretty narrow prior, so that was to be expected. Sample acceptance rates, much, much higher for our gradient sampler than they are for stretch move. Again, not a surprising result based on how these are, how both of these samplers work. And then sort of a measure of the efficiency of this, how long is it actually taking to get our effective samples once we thin by autocorrelation lengths, once we consider the actual time it's taking to get one sample over the other. I mean, neither seems that big, but we are getting slightly larger effective sample size for the gradient sampler than for the stretch move, meaning that at least at these widths, this is slightly more efficient for us to run. And you can even see that the stretch move does appear maybe to get some samples in what could be a secondary mode elsewhere throughout even this small bit of space, whereas the gradient one immediately finds the true answer and sticks there. But when we expand this prior considerably, do gradient proposals solve the issue? Well, no, they do not, and that was sort of to be expected, that if we multiply that by a factor of 10, we're really not getting convergence in either case after either 10 to the 5 samples or about 12 hours on the GPU wall time, whichever comes first. I can tell you that it is the GPU wall time for the gradient samples. Is that too restrictive of a wall time for the GPU? Maybe. You could try extending out further, but it's not going to really solve the issue at this particular prior width. But what about in between? If we start to grid it up and consider multiple spots throughout, we're setting priors at different widths, running similar analysis throughout this, how can we compare the metrics on things like the acceptance rate, on things like its overall efficiency, and whether or not those chains actually converge. I show that here for those 2 different MCMC proposal schemes, and we see that again for the gradient proposals, the acceptance rate do stay as expected, a bit higher. The efficiency gap increases a little bit as we start to increase that prior width. But convergence does become a problem at roughly the same time. And so realistically, if you look at this plot, you can ignore everything that comes after those chains wouldn't have converged anyways. You shouldn't really read into that much at all. So we're really looking somewhere at around like 7 or 8 times this Fisher uncertainty where the samplers that I was setting up started to break down. And that might scare some people. What is actually going on here, if we go back to that same sort of that same plot from the second slide, but now actually calculate the gradient and see which mode it is pointing towards at certain points throughout this grid, whether it is pointing towards the most dominant global mode or a secondary one. You see we have a really sort of narrow ridge where it is going to be more predominantly pointing towards the true value as opposed to a secondary mode. Now that, we can potentially grid this up more and see a bit more structure if we zoom in a little bit, but just to sort of give you a global picture over a wider range of parameter space, what this is really telling us is that gradients alone are likely not going to be the answer for parameter estimation. Again, that hopefully should not come as a huge surprise. This is not an easy problem. It should not have necessarily an easy solution. So what is going to be the solution then if we can't just sort of plug and play this and get our emery posteriors? And there's tons of ways, actually, that we should be able to look into and maybe help improve what we've currently built and tested. For example, why don't we just try parallel tempering? I mean, this is probably the lowest hanging fruit. The infrastructure is already there within the code. It's just a matter of testing it against the nuts routine and the nuts moves that's built in. Because if we are able to sort of temper our likelihood a bit, or have multiple temperatures to sample over, maybe now we can cross over the basins and find the true global mode. We can mix proposal jumps with others that exist within the ARIN infrastructure, combine with things like normalizing flows, other tools from simulation-based inference or machine learning approaches, or just improve search algorithms. It's a give and take between the search algorithms and the parameter estimation pipelines. And these are all things that we are working on. Actually, Curt is giving a talk on the improved search algorithm, or a new emery detection statistic tomorrow. So again, there's work happening on all of these fronts, and it really is going to be a joint effort for improving parameter estimation for emeries in particular. So to summarize, these tools for gradient proposals are incorporated into the ARIN sampler and the Airborne Global Fit. They're currently existing in my dev branch of ARIN, but I'll be working with Michael Katz to sort of combine everything together. It does prove useful in running very efficient parameter estimation when we have narrower prior bounds, but it currently is really not alone by itself able to traverse those degeneracies in the emery signal space. And then lastly, I'll just point out that this was an emery session, but the implementation is source agnostic. You can use this on any favorite Lisa source that you want, and I encourage you to do so. So thank you.
That was very interesting. Questions?
Yeah, nice stuff, Gabe. So you were mentioning, like, on the parallel tempering thing, the dirty secret is that none of the codes that I have for, like, doing any of the analysis I do work without it. Like, it's absolutely critical. Like, the trans-dimensional moves only get accepted really at the high temperatures. Like, the whole thing just doesn't work without parallel tempering, so highly recommend getting in that in there. There's an unpublished paper that I will try and make published that Matthew Digman and I wrote 2.5 years ago. That is a really cool scheme. The theory is based on statistical mechanics for very efficiently and automatically getting your parallel tempering ladder spacing correct. There's other papers out there, like one by Will Farr that's based on the acceptance rate. This one's actually based on the variance of the log likelihood at each temperature, and that gets estimated very accurately, very quickly, and so you can adaptively adapt your temperature ladder in just a fraction, like in a very few iterations, and get the perfect, and that way where you don't need very many chains, because you can span the temperature, you can place them optimally, because otherwise you've got the cost of like hundreds of chains. You don't want that. So we'll try and get that out the door so you can use it, but it's a really good way to space your chains.
I look forward to it.
Yep.
Next week, right?
Yeah.
No.
It's only been 2.5 years.
Okay.
Thanks for making that secret an open secret. Other questions?
For the really cool talk. So all of the kind of algorithms you described, if I understand correctly, are kind of variants on MCMC, right?
Yes.
I'm sure can you tell me about if there have been attempts to try other sampling algorithms altogether, like nested sampling or something?
Have there been attempts? Yes. Have I personally attempted them? No, certainly not in this case. But yes, there's many other ways that you could attack this problem or other sampling routines. Like nested sampling.
Okay. Is it like computationally infeasible?
Nested sampling is computationally quite taxing, and we are already in a very taxing regime as far as computational problems go.
I see. Okay.
Online? No. More? We have time. We have time. Okay, well, good.
I just wanted
wondering, for the gradient component of this, how much is it tied specifically to the few waveforms, or is this kind of waveform agnostic? I think you mentioned it, but I'm sorry, it's Thursday afternoon, I phased out a bit when you're talking about how the gradient is actually computed.
I understand. The gradient code, this stable Emery-Fisher code, is built on off of few.
Okay.
So yes, they all interact with each other. It only works with few,
Okay.
as far as I know, as far as I've used it, certainly.
Okay.
Any more? Okay, well then, let's thank all the speakers again.